want it to be perfect. I want it to be perfect. Nothing in this world is... Oh, that's perfect. Good morning, good welcome, good evening, hello. A little white balance action for you there. Oh, gosh, I'm just not feeling good about this video. Welcome to your Friday Math Minute. I'm recording this on a Saturday. It will probably get posted on a Sunday, but it should have happened on a Friday. So we're going to call it the Friday Math Minute. Let's talk about what we call function notation. What is function notation? Let's say that we had something like y equals 2x plus 3. You may know this is a linear equation. If you don't know it's a linear equation, you can probably tell it's an equation because it has an equal sign, right? So y equals 2x plus 3. What do we normally do with something like y equals 2x plus 3? Usually what we start to do is we say, well, let's set up a table of values and let's see what happens as we change x and y. And that's great. There's no issue with there. And that's a great idea. So let's say I decide, you know what, x could be -2, -1, 0, 1, 2, 3, on and on in either direction, right? I can let x be anything I want. And then I'm going to have to come up with a bunch of y values. Now I've got all this nice space here where I could be doing my scratch work, but it's kind of awkward right now to start writing down what it is that I'm doing. Like I need to say, you know, if x is -2, then y is going to be 2 times -2 plus 3. So that's -4 plus 3 equals -1. Okay, so that gives me an ordered pair -2, -1. If x is -1 instead, then what happens next? Well, now y would be 2 times -1 plus 3, -2 plus 3 equals 1, and so we get -1, 1. And then we can keep doing this, although you can see I'm running out of room here. If x equals 0, if x equals 1, and we're going to get some other values. We're going to see, 3, 5, 7, 9, and so on in any direction. There's nothing wrong with this. This is a nice table of values. We can do something with these values. We can create ordered pairs, or we can recognize these as ordered pairs. What do we want to do with those ordered pairs? We know that we can put them onto a graph, and in this case, it's going to end up making a line. So -2, -1, that goes over here, and then -1, +1, 0, 3, 1, 5. Let's draw a line passing through those points. That's pretty good. And so there it is, right? That is the line y equals 2x plus 3, or at least that's the line associated with the equation y equals 2x plus 3. Well, this is fine. Why do we need to introduce some weird thing called function notation to do this same thing? And the answer, there are a couple different ways you can think about it, but one, obviously all of this here is kind of awkward to do. Sometimes we don't want to have to write all of that down. The whole point of notation is that it's going to make some parts of our job easier. We're going to understand what we mean without writing down over and over again, if x equals this, then y equals that. If x equals this, then y equals that. It can also get a little confusing when we don't use this thing I'm about to show you, function notation. We might think, well, wait a second, why is it that we're saying down here y is -1, and over here we're saying it's +1? Why is it that x itself is changing here? Like, it's just a little confusing what's going on between x and y, especially early on in algebra, when we tend to think, oh, once we've solved x equals 5, that's it, for always and forever, x is 5. Once we have solved y equals -1, that's it, for always and forever, y is -1. But it turns out that's really not true. The whole point of a variable is that it changes. That's why we call it a variable. And so we want some kind of notation that's really going to expose that fact, that's going to show us it's changing. And so that is what we call function notation. So here's how function notation works. Instead of saying y equals 2x plus 3, we say f of x equals 2x plus 3. In other words, this does not mean some variable f times some variable x, although in other contexts it might mean that. In this particular case, it means we have a function of x. We could say a function of x such that you double x and then add 3. In other words, the function notation is highlighting process. And I guess I should take a step back here. What is a function, right? Why are we interested in them? There are lots of definitions of functions, but one of them is that it's a mathematical object that takes inputs and produces outputs. So the other nice thing about function notation is it's really highlighting for us that's the input, and then this whole thing here is going to give us the output. So when we want to know something like, well, what's f of 3, let's say, what we really mean is 3 is going to be our input. The rules said to double that input and then add 3 to it. 2 times 3 is 6, 6 plus 3 is 9, and so what we can say is that f of 3 equals 9. Now, that should be familiar to you because that's exactly what we did a moment ago when we figured out that 3, 9 was one of the ordered pairs for this particular function. In fact, all those input-output pairs can be represented using function notation. We could say things like f of -2 is equal to -1, because when we plug -2 into the rule, into the function, we get back -1. F of 0 was 3, right? And so this corresponds to the ordered pair 3, 9, just like this corresponds to the ordered pair -2, -1, just like this corresponds to 0, 3, and so on and so forth. So the function notation helps us understand a little bit better the relationship between inputs and outputs. It helps expose that relationship a little bit better, just like it helps expose is a weird word here, surface, it reveals, it shows us the nature of variables. They're things that change, right? The x value here is our input and it's changing. Sometimes it's 3, sometimes it's -2, sometimes it's 0, sometimes it's pi, sometimes it's -1,000, sometimes it's 1,000,000,000. It can be whatever we want. And then the output over here, well, that's our y variable, right? But again, it's changing as we go. I guess there are a few other interesting things that you can do with function notation. So sometimes what we like to do is say, well, what's the value of the function at a certain point? Let's say f of 6. But if we had to move the whole thing down. In other words, if you imagine we're still looking at this same line, f of x equals 2x plus 3. F of 6 on that line, you'll recall, was 2 times 6 plus 3, or 12 plus 3, or 15. If we went back to this line and we just kept going, we would end up at 6, 15, up to over 2, up to over 2, up to over 2. There it is, 6, 15. So if we had stayed on that line, we would have eventually gone through 6, 15. F of 6 is just a way to write the value 15 without writing it. We know f of 6 is the same as 15. And now we're saying, well, imagine we're actually going to move that value down 5 units. So we're going to end up moving the whole function down 5 units. And later on, this is going to help us understand transformations in the plane. When we move things up and down, left and right, when we stretch them out left to right, up or down, when we squish them down one way or another. And so function notation is also going to help us think through those transformations in the plane. So it's useful for a number of different things. I wouldn't say it's the most exciting thing on earth, but that's all that's going on there. It's a way to write about inputs and outputs. It shows you that the variables can change. X is changing, and when it changes, it produces different values for y, which is also changing. Highlights process, and there's lots of other good stuff that we're going to use it for in the future. I hope that's been helpful. That's all I've got for you today. Make sure to comment down below with any questions. Surely I messed up something terribly. Yeah, let me know. Thanks so much for watching.